Wayne Thatcher is going to give a presentation on the geodetic data that are available in this central coastal region. Jessica Murray Moriald and wasn't able to make it, and Wayne was kind enough to step in and present her and yours information.
Yeah, let me first of all make clear that this is largely Jessica's work. She leads the GPS studies in the Central California Coast Ranges. She's been the project leader of the PG&E USGS CRADA on this effort over the last 4 years, and I will do my best to represent what is largely her work. I've been involved in it in a minor way, and will be doing more of the modeling in the future. In the large-scale context of California, as many of the previous talks this afternoon have emphasized, one of the major questions is, what's the partitioning of the strain in the Central California Coast Range region? In particular, the partitioning between the strike slip and the reverse faulting. There are a number of different tectonic models that have been proposed to account for this. What Marcia McLaren and Woody Savage suggested over 10 years ago now is indicated on the left, and their idea was that crustal blocks were rotating clockwise, and uplifting and producing reverse slip and compression roughly perpendicular to the strike slip faults. A more recent model that Jeannie Hardebeck has come up with based on her studies, of which we heard several recent updates earlier this afternoon, has a slightly different view of the origin of this partitioning, with perhaps the compression being oriented more east-west. These are the kinds of working models that we have in mind from the geodetic standpoint to try and understand better and quantify this partitioning. There's what seem like a lot of GPS sites in the Central California Coast Ranges, particularly in the last 5 years or so, with the establishment of the Plate Boundary Observatory, with the support that's been provided under CRADA funding to put in repeated survey mode stations, and then semi-permanent GPS sites, that is, ones that are occupied continuously for a month, then the instruments move to another site, and then a year is filled in kind of 50% of the time. And these prove to be almost as good as the permanent GPS sites. So in the study area, indicated by this polygon, there are something like 55 stations that are available for study. It's an otherwise very pristine, clean area to investigate because it's far enough away from the San Andreas Fault that the effects of the fault directly from strain accumulation are small, and the effects of the coastal faults presumably can be studied a little bit more easily. However, 2 tiresome earthquakes occurred in the early 2000s, the San Simeon earthquake and then the Parkfield earthquake. And those earthquakes contaminated the GPS signals in ways that I'll show you in a moment. Okay, you can look at it right here. So this is a time record from 2001 to 2007 of a continuous GPS site. I think this one is near Parkfield, that shows the offsets that occurred at the time of the San Simeon earthquake and then at the time of the Parkfield earthquake, and also the transient movements that followed those earthquakes. In order to understand the steady state deformation pattern, the effects of the earthquakes themselves, the coseismic offsets, and the transient movements that follow them have to be corrected out. And this is, as you might imagine, something that can be done to first order, but imperfectly. And so Jessica has proposed a method that accounts for just instrumental offsets due to changes in the design of the station, the coseismic offsets due to the earthquake, and an approximation to the post-seismic transient motions, as well as seasonal effects that also can contaminate the data. And this could be done both with the continuous data and the survey mode data. The standard approach, if there's data both before and after these earthquakes, is to include all of this information, and in particular, try to compare the pre-earthquake velocity, this slope here, with the post-earthquake velocity that has been corrected in the manners that I described to you. When this is done, the comparison, again, to first order, this is the rate estimated using only the pre-earthquake data, and this is one in which all of the data are used, is generally good. Although the points would lie on this diagonal dotted line if the fit was perfect. I think the red points are just ones near Parkfield. The vertical is always much less precise than the horizontal, and we don't use it in any of our analysis thus far. But the difficulty is that in making a first-order correction for the post-seismic effects, most people, including Jessica, have fit a logarithmic function to the data with a one-year time constant. And this is what the functional form of this exponential decay is. This is 1 year of data detrended, and I think you can see that there's still effects in these data that are continuing transient deformation that we'd really like to get rid of, but we don't understand well enough to be able to do so. So Jessica's approach in this case, when there's information only after the earthquake, and you don't have pre-2004 observations to get the steady state velocity, is to just assess the uncertainties and enlarge the error ellipses for those data. When she does that, it's as I said, straightforward if you have pre-earthquake data, more complicated when you have only post-seismic data. The result is this particular velocity field, the differences in the points are not important, except that the most precise are the continuous GPS sites, but again, they have post-seismic contamination in them. The green are the survey mode, and blue are these semi-continuous sites that the USGS has installed over the last 3 years. If we zoom in on the central coast ranges, then this is what the velocity field looks like. The details, again, are not too important. I think you can see from the internal consistency of the data that it's generally quite accurate. We would regard this as a pretty good velocity field for the kind of studies that we do at the USGS and others do elsewhere. However, we're looking for fairly small signals in the central coast ranges, so the task is rather more difficult. The approach that we have begun to model the data that I've shown you is so-called block modeling. It divides up, in this case, Central and Southern California into elastically deformable blocks that are, in some cases, locked along their boundaries because there's no earthquakes occurring. So strain accumulation is occurring as a result of, for example, the San Andreas Fault being locked in Carrizo Plain. When we apply this approach to the GPS data set that I've just described to you, we can determine the rotation rates of each of these blocks, and if we choose, the strain rates within the blocks, if there's any within the uncertainties of the observations. And we've used an augmented data set supplied by the Southern California Earthquake Center and PBO continuous GPS sites in addition to the ones that are included in our study. When we do that and take as the simplest working hypothesis that the selenium block is a single block, is not deforming, then we get these estimates of the movement rates across the principal faults, for example, 4 millimeters a year across the Hosgri-San Gregorio trend, 10.5 millimeters across the Eastern California shear zone. We, however, within the selenium block, see significant residuals. So this plot shows the misfit between what this model predicts and what we observe. In particular, in this region to the southeastern part of the supposed selenium block, the residuals point in the southerly direction at about 10 millimeters a year. This is a very large uncertainty. Something is wrong. And in compensation, you have residuals pointing northward in the rest of the block. It's just a least squares inversion, basically. So there's something not quite right with this null hypothesis. Previous investigators, a study by Becker et al. And Mead and Hager, similarly found large residuals in this region, and we can point them out here. And in this particular study, an ad hoc GPS block was added to reduce the residuals. But the difficulty with this, and we've applied this, here's our edition of the Big Pine block, is that there's no geologic evidence for such a boundary. And indeed, if it were to exist, the model would predict extension, oblique extension across this boundary for which there is no geologic evidence. So again, there's something that we're not getting in the results that we've obtained so far. But if we move boldly onward and hypothesize the existence of the oceanic, an additional block bounded by the oceanic fault, we can reduce the residuals slightly, but the relative motion across this boundary is extremely small, of the order of a millimeter a year or less, and we still have this questionable Big Pine block included in our model. The rate on the San Andreas Fault is slightly higher. In these models, the neck bone is connected to the ankle bone, and the ankle bone is connected to the knee bone. So you change the block model in one place, and you affect the results elsewhere, and that's one of the dirty little secrets of this kind of analysis. The efforts that we plan to use in the future are to use a more realistic block model for California that is being developed under USURF-3 in an effort that a number of us are involved in, and then embed the Central Coast Ranges in that model, and then look at our results. And Jess is just involved in beginning to do that now. The results seem promising. They're different than we found earlier, but still preliminary. My time's up, so these are my conclusions. So far, we see little relative motion taken up on the boundaries of this proposed oceanic block, and that it's within uncertainties indistinguishable from the Selenian block. There's no certain evidence that we've found of compression, although Jessica emailed me 2 days ago and said she'd done a run that seemed to indicate some compression in her model results, but this is very preliminary. The next steps involve, as I mentioned, incorporating this consensus block model for California, looking at a number of different block geometries and assessing how much this influences the slip rates on faults that you geologists tell us are active, and to search for evidence of compression that must exist at some level. And what geodesy will be able to do is to place some bounds on those, and that's our future work plan. I'll stop there now, and thank you very much for your attention.
Yeah, I have a question about the USURF3 consensus block model. So the USURF team is heading towards a single block model to be used in all runs, or do they have alternatives A, B, C that they're developing?
They've zeroed in on a single block model.
And can you, and its characteristics for our area, it looks from the figure on the right that it does recognize faults bounding either side of the San Luis range.
Well, this is a little complicated. The GPS blocks are the ones that have yellow boundaries, and the one shown in red is the geologist's block model that Tim Dawson and Ray Weldon were kind enough to construct for us as sort of our starting point in coming up with a geologically defensible block model. So there are a lot of faults there in the quaternary active fault map. Only a subset of those are considered in this USURF3 model.
The block boundaries shown to the left, those boundaries do coincide with the consensus USURF model at this point, or are there?
Oh, this one here?
Yes.
That's a good question that I'm not sure of the answer of at this point. This has evolved over the time since this figure was first prepared in January. So I won't promise you that it's exactly the same. But the goal is now to use the consensus model, which has been established and as the standard, and that's Jessica's latest modeling has used that.
I also hate to ask this question, but I will just for the record. What are the chances that geodesy will provide constraints for slip rate and slip direction on a fault such as the Los Osos fault?
I think the answer at this point is that we really don't know, and that's the subject of doing a number of different block scenarios, sort of micro-block scenarios, seeing what the GPS data tells us about the motions of these blocks and what the constraints are. I If it's slipping more than a millimeter a year, then I think we have a shot at it. The evidence elsewhere suggests that that's kind of the precision with which fault slip rates can be estimated via these block models. If it's less than a millimeter a year, then and other closely spaced faults are also moving, then distinguishing that fault's motion from adjacent ones is rather difficult, because the faults are not slipping at the surface now. The simplest model is that they're locked in the upper seismogenic zone and then slipping freely at their long-term slip rate at greater depths. The canonical model for the San Andreas fault, for example, locked in the upper 15 kilometers, then freely sliding at greater depths. So that means that any effects of continuous fault slip at depth are smeared out at the surface. And that's why it's such a tough problem for closely spaced, low-rate active faults.
The one fault that, given what you just said, we should be able to resolve that something's happening would be the San Simeon-Hosgri fault system, which presumably has 1 or more millimeters per year slip.
Yeah.
Can you say anything? At what point will we know how much unresolved slip might be occurring offshore? In rough order of magnitude, even, just to provide broad constraints on uncertainty.
My own opinion is within several years, when we're able to test out these different scenarios using the kind of the block model paradigm, we'll be able to estimate slip on the San Gregorio-Hosgri fault within a couple of millimeters a year. That's kind of that's my gut feeling.
That would be great. That's within the context time frame of our study, several years. So,
and I remember the comment this morning that the uncertainties that exist now are for the slip rate on that fault are between 0.5 and 6 millimeters a year, and I think we'll be able to improve on that.
Yeah, that would be outstanding.
Yeah.
Is that based on the way the models move, the way the blocks move, or is it measurement across the San Simeon and San Gregorio?
It's both, because
you don't have much on the west side.
You don't have much on the west side, exactly. So it's necessarily model dependent, because the Hosgri-San Simeon fault is not slipping at the surface. The effects of its slip rate are, again, smoothed out over a broad area that has a scale length of the locking depth. And on a time scale of a decade, it would be very useful to have ocean bottom GPS to be able to get far enough to the west of those faults, so you don't need to worry about these local strain accumulation effects, and you would be able to directly see the slip rate on the fault. As perhaps many of you know, in the aftermath of the Tohoku earthquake, there's been a lot of discussion in the earthquake science community about expanding ocean bottom GPS because it's provided unique information for the Tohoku earthquake and is likely to provide equally important information on offshore, nearshore faults off the west coast of the United States and off California.
If PG&E is putting in ocean bottom seismometers, can you co-locate GPS stations with those?
I think the short answer is no. It's because you don't have a GPS instrument on the seafloor. You have a transponder that sends signals to sonobuoys that are on the ocean surface, and a ship that is recording the signals from those sonobuoys. So it's a very different kind of technology.
Okay.
The only group that has really made a major effort to do that in the United States is at Scripps.
Okay. I had earlier, Marcia, when she showed the seismic network, you had a co-located up near Ragged Point along the San Simeon Fault. It was co-located with a GPS station. Is that one of Jessica's stations, a permanent station? And at the scale of your map, Marcia, and maybe Wayne, you know, I couldn't tell exactly where that station was. It looked like it was west of the main trace of the San Simeon Fault, but as Catherine and I at least have mapped the San Simeon, there's a number of branches. It's almost like it's within the San Simeon Fault zone.
It is. Is this on? Hello? Yes, it's just, it's basically, it's feet away from the main trace of the San Simeon Fault zone, where it starts sort of to get those branches on the west side.
So that might...
It's a little close. It wasn't the ideal spot, but it's where we could actually do it because we had our Piedras Blancas station there.
Yeah.
Yeah.
But we might be missing, if that station's used to help try to constrain rate across the San Simeon, Hosgri, San Gregorio system, that might be missing some San Simeon Fault on the west side.
Yeah, and as I emphasized earlier, because those faults are locked, not slipping at the Earth's surface, it doesn't matter a whole lot whether you're on one side or the other, but it's a second-order effect.
Are there any other questions for Wayne? Anybody have any? Steve?
I've got one other also. There's a proposed station on an offshore rock called Pecho Rock that was recently permitted. And it's similar to what Bill just mentioned for that permanent station. It's on the west side, southwest side of the shoreline fault.
Yes.
Given that we have it's essentially right over the seismic source, and it's one of the things we're wondering is there any value in setting up a creep array? Can you leverage it? Are the GPS stations going to be accurate enough to use to evaluate whether the shoreline fault is creeping? Or should the pursuit be for other technologies for evaluating the presence or absence of creep?
Well, again, it depends at what level it would be creeping. If it were creeping at 1 or 2 millimeters a year, then right to the surface, then stations to the west and to the east of the fault should be able to detect that. I think it's